Okay, so I thought since I got kind of cut off the other day while presenting the Schroder-Bernstein theorem that I'd give it another shot in a pen cast. So if you remember the setup, what we want to prove is that if we're given two sets, and I'm going to call them X and Y here, I realize I called them A and B in class, but it doesn't really matter. If we're given two sets and we have injective maps, in other words, we have one-to-one maps, this is one-to-one, and this is one-to-one, then X and Y have the same cardinality, they have the same size. That's not quite what it says in the notes. The notes say that there's a bijective correspondence, which is sort of equivalent for sets. But we're going to be able to construct this bijection from this version of the Schroder-Bernstein theorem. So here's the proof. Here are the assumptions, of course. We're given two sets, and we're given the injections. So that's the setup for the Schroder-Bernstein theorem. F is a one-to-one map, and G is a one-to-one map from Y to X. And of course they're injective. It has to meet that. And my setup was this. I said, consider the mapping telescope. And here's what that G kind of fell apart. But here's the mapping telescope. If you think of, this is the set X here, and this is the set Y here, this is the set X here, and this is just sort of a shorthand representation where we're just applying G to every element of Y here and mapping it over to here, right? And we know we have that injective function. So that's the mapping telescope that starts with X, and then we have a similar mapping telescope that starts with Y. And the thing I wanted to consider was how elements are related across these mappings. And so I wanted to think about the ancestry of any of elements in X, for example. So if I pick an element in X, let's call it little x. I called this x1. If it's in the image of G, then there's some y1 in Y that maps to x1. And if y1 is in the image of F, then there's some x2 in X that maps to y1. So in other words, f of x2 is y1, and g of y1 is x1. And we can look at all the elements of X and consider their ancestry, and we can look at all the elements of Y and consider their ancestry. So just to be really clear, you'd pick some element Y in Y, and we'll call it y1. And if that's in the image of F, then there's some element in X that maps to y1, and I called it x1. And if x1 is in the image of G, then there's some y1 here that maps, or y2 that maps to x1, and so on, and we can figure out the ancestry of these things. And really we're only that's 2. Really we're only considered with the length of the ancestry. So now we define the following sets. We define x infinity to be all those elements of X that have an infinite ancestry. So in other words, X is in the image of G, whatever that element in Y is in the image of X. So as you build your way up, there's no place where this chain breaks down. X odd is all elements that have an ancestry that's an odd length. So odd length would be 1, 3, 5, 7. And X even is all elements that have even length. And similarly, we can do a similar operation for Y even, Y odd, and Y infinity. And my claim was that these sets partition, well, these sets would partition Y, and these sets partition X. In other words, every x element would have to be represented somewhere in these three sets, and every y element would have to be represented somewhere in these three sets. And now I claim that F is a one-to-one and actually onto map from, if you restrict it to x infinity, to elements of y infinity. And it's easy to see why that's true. If I have something that starts with x1 and has an infinite string, an infinite ancestry, then if I just sort of cover up x1, y1 has an infinite ancestry as well. So there's a one-to-one correspondence between things with infinite ancestry. Maybe slightly more difficult, but actually the same idea, is that elements in x odd are in one-to-one correspondence with elements of y even. In other words, if I have something with an odd ancestry up here, it'll end in an x, right? If I just sort of cover up that x, then there are an even number of them left, and that element would have a even ancestry in y. Where'd that go? Oops. I don't know why that skipped around like that. And then similarly for G mapping from y odd to x even. Those maps are, by definition, by assumption actually, they're one-to-one. I've just argued that they're onto, although you can do a more formal proof if you like. And this allows us to define a bijection. Our bijection is defined in the following way. I'm going to call our bijection H. This is a bijection between x and y. And here's how H of x will work. We'll use f of x whenever whenever we have an element of x odd. We'll use f of x whenever we have an element of x infinite. And we'll use g inverse of x whenever x is an element of x even. And you might note that that does have an inverse, right? Any one-to-one function. Well, I hope to demonstrate that they're one-to-one and onto, or at least argue persuasively. Since I can create this bijection here between x and y, this bijection here, x and y have